Hello everyone, my name is Franco Pucci. I'm the technical consultant for the STS Association. Welcome to Training Video Series 2, where we will explore the companion specifications. I hope you find these videos helpful. In this video, we will look at the STS600-8-6 companion specification. Please refer to the relevant document for detailed descriptions. And the document is STS600-8-6 Hardware Security Module API. The standard specifies a set of service request and service response message pairs for data exchange between a client application process and the HSM application process. It does not specify the lower layers of the communication interface protocol stack, which is left to the HSM manufacturer to implement in accordance with market requirements. All commands apply to both vending HSM devices and manufacturing HSM devices unless otherwise stated in the document. This API standard assumes that the reader has reasonable knowledge of the STS ecosystem, in particular should be familiar with the IEC 62055-41 as the core STS standard, which defines tokens for the transfer of credit and other instructions between a point of sale and a meter. The key management process described in STS 600-4-2 and its associated data formats. The STS 600-4-2 defines the key management infrastructure and associated process that manage cryptographic keys. The reader should also be conversant with the terms, definitions, and abbreviations widely used in the STS standards. There are two firmware types for an HSM, manufacturing and vending firmware. The command groupings for each are shown below. You have general and diagnostic commands, and they appear in both the vending firmware for security modules and the manufacturing firmware. Operational key management commands appear in both as well. STS transfer credit commands will appear only in the vending firmware and not in the manufacturing firmware. STS management commands appear in both, and then STS manufacturing commands appear not in the vending firmware but only in the manufacturing firmware. Vending firmware is used by a token vending system to create STS tokens. Manufacturing firmware is used in a manufacturing environment to introduce keys into meters. Manufacturing HSMs can issue management tokens but not credit tokens, and include a special command to change a meter from a DITK to a default common or unique key. To comply with the international hardware HSM security requirements for key component entry, the DITK key components are loaded by the meter manufacturer via a dedicated serial port that is physically separate from the command interface port. The HSMs may support additional commands, including proprietary commands necessary for the production and maintenance of the HSM. These commands are out of scope of the standard. Key management in the HSM, and for that please look at STS 600-4-2. You get a public key by email. You then issue the command smkc, which is generate a VK load request. The VK load request comes out of the security module, which you will then send to the KMC by email. The VK load response is then generated by the Key Management Center and sent back to the requester by email. You then load the VK load response using an SMKR command into the secure module. At this point, all current keys are deleted and a key exchange key slot is established. Then using the SMKL command, you load all the vending keys. The HSM stores each key in a register. The register is unknown. The HSM will merely store it wherever it finds place. At the end of the session, when you've loaded all the keys, you issue an SMKF command. This closes the session, but only for vending HSMs. For a manufacturing HSM, the session will remain open. You do not issue this command. And the reason for that is because in a manufacturing environment, you could have 1,000 supply group codes that you are supplying meters to, and you cannot load 1,000 of these vending keys into a security module, so you can load a section at a time, then unload that section and load a different section, etc. Remember, each VK load request and response is usable only once. What is a KEX slot? We'll talk about that now. So it's a key exchange key slot. During a management session, a key exchange key, or KEK, is established between the HSM and the KMC. It's almost like a shared secret between them. The KEK is stored in a KEK slot, also called a KMC slot, and that slot is assigned to the KEK from the start of the key management session. Each HSM has a number of KEK slots and can thus receive vending keys from multiple KMCs. The table below shows the KEK slot current state and the KEK slot next state after the indicated command. And you can look through this yourselves, but essentially what it says is it starts off with a KEK slot current state of none, nothing has happened. You issue an SMKC command and the KEK slot goes into a pending mode. Any of the other commands shown there's no change to the KEK slot unless there's an error. Then if you go from a pending state and you issue an SMKC command, it remains in pending. If you issue an SMKR command, it goes into loading state and all the rest remain no change or pending. And if you issue an SMKF command, it goes into active or none if there's no keys, and so on. You can read through that on your own. During a key loading session, each vending key is loaded into the HSM and stored in a vending key register. The vending key register is automatically allocated when the vending key is loaded and is identified by a register number. A vending key is uniquely identified in the STS ecosystem by the combination of its supply group code and the key revision number. An attempt to store two vending keys having the same supply group code and key revision number combination will overwrite the currently stored VK, even if they originate from different key management centers. The token ID to RTC, or real-time clock window, is a 7-day range around the HSM's real-time clock. Attempts to issue an STS token with a token ID outside the window will be rejected. This ensures that the date and time of the token is close to or reasonably close to the HSM's real-time clock. This feature can prevent accidental vending of old or wildly wrong tokens. The window is fixed at a 7-day period and cannot be disabled. We look at the communications protocol. The request message essentially has a header, a payload, a checksum, and a terminator. The header is 5 ASCII characters. The payload is PTVD encoded. We'll talk about that a little while later. Checksum is 4 hexadecimal digits, and then the terminator is a carriage return. In some messages, payload is not present, and in some messages, payload is not PTVD or printable type value delimited encoded. These are made clear in the document itself, which ones are and which ones are not PTVD encoded. The response message, very similar. It has a header, which is 5 ASCII characters, a status, a payload, a checksum, and a terminator. Again, in some messages, payload is not present, and in some messages, payload is not PTVD encoded. If we look at an example with no error, we send a request message, get identification, which is an SMDI. There's no payload, there's a checksum, and there's a terminator. The response message with no error comes back and it's SMDI, except this time it has an exclamation mark between the SM and the DI. Status is 00. Payload is P94001234. Then there's a character, delimiting character, which is the tilde character. And then there's a PSTS65V00, and again the tilde character, a checksum, and a terminator. A status of 00 indicates that there's no error encountered. 94001234 is the secure module ID, and STS65V00 is the firmware ID. Let's have a look at an example with a standard error. We send an SMGA. The payload is N12, the checksum 8602, and a terminator. The response message with a standard error is SMGA, status 22, so the error number is 22. There's no payload, there's a checksum, and there's a terminator. The status of 22, if you look in the document, is equates to CSP record empty. In other words, vending key register 12 does not exist. In certain cases, an error can be returned where the response header is set to GLER, regardless of what the request header was. This is generally used for errors where the request format or integrity checking fails. For example, we send an SMDI 0000 and a carriage return. Now, the 0000 is supposed to be a valid checksum, but obviously the 0000 is not. So the error status coming back is error status 20. You can see it in the response in yellow, which indicates a checksum error. We can also send an SM ? Junk with a correct checksum this time. The error coming back is error status 21, invalid request header, because the secure module doesn't understand the command or the payload junk. The last one we look at is the extended error response, where you can send or you get a response which is SM, for example, KC, and there's an EE. The EE tells you that there's an extended error coming back. It's a printable string, and the error itself is SM.1B.1 : load request, speed limit enforced, try again in 60 seconds. So it gives you a little bit more information. What is PTVD? PTVD encoding is essentially a string of data which is delimited or by certain start or headers, and the headers for a number, for example, is an N. An N signifies a 32-bit integer in the range 0 to that large number there, and leading zeros are not permitted and negative numbers are not supported. If you look to the right, a 0 is represented as N0. The tilde character at the end is the termination character. A 1 is represented as N1, and 99 as N99. N01 is not allowed because it has a leading 0. The P is a string as a sequence of 0 to 65535 printable ASCII characters. So on the right you can see, for example, P, and then my KMC name is a valid printable string. The date time starts with a D, and that's in UTC time zone format using the Gregorian calendar, and is encoded as century, century, year, year, month, month, day, day, hour, hour, minute, minute, second, second. And then hex starts with an H, and that's an octet string as a sequence of 0 to 32767 octets. So on the right you can see an example. H3D7EC8 represents the hex number 3D7EC8. In the next video we will look at the supported commands. This brings us to the end of this part of the video series. I hope you found this video helpful, and I hope to see you for the rest of the video series. Goodbye, and see you again soon.